Okay, so let's have a look at this problem. We have a particle that's moving along a line, and we're given its velocity is 3t minus 5. And we're interested in the displacement and the total distance traveled for that particle over the interval where time is between 0 and 3. So the way that you would go about answering this question really depends on your level of expertise in calculus. So I'm going to explain it both ways, kind of the most basic way and then the fancy calculus way. So the first thing we have to do is let's draw a graph of v of t. So it's 3t minus 5, which is just a fairly basic linear equation. And then we just want to remember anytime velocity is negative, that means the particle is moving backwards. Negative velocity, the negative part is just directional. So that means from time equals 0, which is right here, to time equals 3, in this interval, from 0 until 5/3, since the graph is below the y-axis, that means the velocity is negative, and that means the particle is moving backwards. But then the particle switches at time equals 5/3, and the particle starts moving forwards because the velocity is positive. So it went backwards and then it went forwards. So it traveled a lot of distance, but it didn't get very far because it went backwards and then it retraced its steps, if you will, and then it went forward. So let's see if we can figure out each question. So displacement. Displacement is how far you wind up from where you started, not how long did it or how much distance did you travel to get there. It's literally if you go from point A to point B, how far is point A from point B? All right. So to find that answer, we're going to find area. The area under a velocity curve is the distance that it travels. So if we want displacement, all of the time when the particle is going backwards, which would be this, would be the total distance, would be all of that area in the blue. And then to that, we would want to add on all of the distance that it traveled going forward, which is going to be all of this in the black. And so we can see that that's actually two triangles. So the blue triangle, the area for that blue triangle, area of a triangle is 1/2 the base times the height. So base, and then this is the height. The base of the triangle is 5/3. That's just the x-intercept on this function. If you plug in 0 for v of t, or for the y value, then t would be equal to 5/3. And then the height is of the triangle is this distance here, which is 5 is the actual height, but we're going to actually count it as negative because the particle is moving backwards. And so we want to show that it has backwards motion. So that's negative 25 sixths. There we go. Negative 25 sixths. Okay, so it went backwards 25 sixths feet or inches or whatever the units is. Okay, then now let's look at the part where it's going forward. It has forward velocity from this point forward, so in the area, to find that from time equals 5/3 to time equals 3, it's moving forwards. So to find the area that under the curve, which is the distance that the particle travels in the positive direction, we're going to find the area of that black triangle. So the base would be 3 minus 5/3. So that's going to be 9/3 minus 5/3, which is 4/3. So the base is 4/3 of the triangle, and then the height is going to be 4. So that is 16 sixths total. Okay, so if we want to find the displacement, what that tells us is for the displacement, right, the particle traveled backwards, so went negative 25 sixths, and then it went forwards 16 sixths. So it didn't travel as far forward as it had backwards. So we're going to expect a negative answer because we know that the particle never got back to its starting point. So it went backwards 25 6 and then only went forward 16 6. So the difference between those is negative 9 sixths, which if you simplify that down is negative 3/2. So what that tells you is the particle wound up to the left, because it's negative, of its starting point 3 halves, which is 1.5 units from its starting point. All right, so the displacement is 1.5 units left of the starting point. And if it started at the origin, that would be where I think it did say. I think that would be where it started from. Okay, so we'll just say the origin / the starting point. Okay, and then distance traveled, the total distance traveled. So we've done most of the work to answer this. The total distance traveled is literally how much distance was actually covered in the whole entire trip. So if the particle was trying to get from point A to point B, really you should just walk from A to B, right? But instead, the particle went backwards a whole lot and then forwards a whole lot. So it traveled a larger distance. So if we want to find the total distance traveled, I always call that TDT, we'll take, it went 25.6 units backwards, but we don't care about the direction. Like you can think of it if it was walking, 25.6 as how far it walked. And then it walked more. It walked 16.6 in the other direction. But here we're going to add those because we're trying to find the total distance that the particle actually covered. So when I add those together, I get 41/6. And so that would be 41/6 total units would be the total distance traveled. All right, so that's kind of doing it using basic geometry with a little bit of a calculus twist, because of course you have to understand what we're doing in terms of calculus. But of course, there's a much easier, faster, more efficient way of doing this. This is what an integral calculates. A definite integral, when you find the integral from 0 to 3 of v of t dt, that calculates the displacement. It calculates the area under the curve of velocity from 0 to 3. And just like what we just did with finding the area of the triangles and sines, the integral takes care of that for you. So in this case, we're going to integrate from 0 to 3. And then the function is 3t minus 5 dt. And I think what I'll do is let me slide this down, the whiteboard down. No. Oh, there we go. Sorry. That took a little bit of work there. Okay, so I will do it down here so you can see this a little bit better. So from 0 to 3, and then our velocity function was 3t minus 5. And then, of course, we need to put in the dt. We can put parentheses around that. So we need to find the antiderivative. The antiderivative of 3t. So remember, you always bump the power up by 1, and then you divide by that new power. So we wind up with 3/2 t squared. And then minus, and then the antiderivative of 5 would be 5t. And we're integrating from 0 to 3. So we are going to use the fundamental theorem of calculus. We are going to plug in the upper bound, which is 3, into t. So I'll get everything ready. Copy that. We're going to plug in this upper bound of 3. All right, and then we are going to plug in the lower bound of 0 into 3/2 t squared minus 5t. We're going to plug in 0. All right, and we're going to simplify this. So in this case, we're going to wind up with 27/2 minus 15 minus, and then all of this is just 0. So we have 27/2 minus 15. 15 is the same thing as 30/2. So we wind up with -3/2. Hey, it's the same answer we got by just using triangles. But we can see that we can use calculus, integrals. Definite integral will calculate the displacement of a particle when you take the integral of velocity. Okay, so then for total distance traveled, that one gets a little bit more complicated when you go to use an integral. What you're going to want to do is you're going to want to integrate velocity. But here's the thing. We want to think of this as the absolute value of velocity. Because remember, velocity, positive velocity means it's moving forwards. When velocity is negative, it means the particle is moving backwards. When we're interested in total distance traveled, we want all the distance, whether it's forward or backwards, it doesn't matter. So we wanted to disregard the sign. We're going to make it all positive. So if you go to graph what this would look like, right, it would be that same function from up above, but anywhere where the graph was negative, we would now flip it and it would become positive. So it would look like this. So essentially, we would be finding this blue area, but instead of it being below the x-axis, it's now above the x-axis. And then we'd be finding this black area still. All right, so you can do this integral on a calculator. That's probably the most efficient way if you're allowed a calculator for this problem. The other option is to use geometry, which we essentially already did by doing the problem up here this way, or to break this up into two integrals, because this is the absolute value graph has a point that is not differentiable. So it's a little bit tricky to do it by hand. You'd have to actually use two separate integrals. When you do that, you'll get the same answer that we got before, which was 16/6. All right, hopefully that helps and makes sense. And there is the answer to the question. Yay, math.